Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is our next module, problem number 25. Okay. Fluid mechanics, problem number 25. As usual, we first come towards statement. The maximum depth D max, where max is written as a subscript of D. Okay. The maximum depth D max that a diver can snorkel is set by the density of the water and the fact that human lungs can function against a maximum pressure difference between inside and outside the chest cavity of 0.050 atm atmospheric pressure. What is the difference in D max for fresh water and the water of the Dead Sea? The saltiest natural water in the world, with a density of 1.5 into 10 raised to the power 3 kilogram per meter cube. Okay. Dear students, here one density is given, and for other density we will consult a table of densities. Okay. For our better understanding, we read the statement once again. Okay. The maximum depth D max that a diver can snorkel is set by the density of the water and the fact that human lungs can function against a maximum pressure difference between inside and outside the chest cavity of 0.050 atm, that is atmospheric pressure, atmosphere. What is the difference in D max for fresh water and the water of the Dead Sea? Okay, within bracket it is provided that the saltiest natural water in the world, with a density of 1.5 into 10 raised to the power 3 kilogram per meter cube. Okay. Dear students, now first we go to table of densities and decide which other density we should choose. Okay. This is the table. Okay. Dear students, here it is given that water at 20 degree centigrade and 1 atm, 1 atmospheric pressure, is 0.998 into 10 raised to the power 3 kilogram per meter cube, while other density given is 20 degree centigrade and 50 atmospheric pressure. Okay. This is 1.000 into 10 raised to the power 3 kilogram per meter cube. Okay. Then it is given that sea water at 20 degree centigrade and 1 atmosphere is equal to 1.025 into 10 raised to the power 3. Okay. All these three densities relate to density of water, and dear students, this density, that is density of water at 20 degree centigrade and 1 atmosphere, that is 0.998 into 10 raised to the power 3 kilogram per meter cube, is our required density. Okay. That is to say, among the above this density of ice is given. Okay, so it may also be treated in broader spectrum within density of water in a different shape. Okay, so dear students, among these four densities we will choose this second density 0.998 into 10 raised to the power 3 kilogram per meter cube. If we want to exclude 10 raised to the power 3, then we can simply write it as 998 kilogram per meter cube. Okay, so I think this point stands solved. Okay, that is to say, four densities are provided in this table which may be treated as relevant, but the most relevant among these four is the second one, which is 0.998. Okay, now we move on to solution. Okay, solution. Dear students, before starting solution, definitely first we will have to develop a foundation on which our solution of the problem will lie or depend. Okay, so in order to construct that foundation, we define a specific situation which covers the whole scenario provided in this module. Okay, the pressure P at a depth h in a liquid of constant density rho due to the weight of the liquid is given by pressure P equal to rho g h. Okay, what is rho? Constant density. G is acceleration due to gravity 9.8 meter per second square, and h is the depth h. Okay, where g is the acceleration due to gravity. Okay, we know from table of densities that density of fresh water equal to rho FW, that is fresh water equal to 998 kilogram per meter cube, and density of seawater which is provided in the statement is equal to rho SW, that is seawater equal to 1500 kilogram per meter cube. Okay, dear students, density of fresh water, we have chosen this density among four densities provided in the table. Okay, it still renders enough material to consider why we have chosen this second density among the four densities of water provided in the table. Okay, anyhow, we do not go in further detail. It is sufficient to describe that among those four densities we have chosen second density as the density of fresh water. Moreover, 1 atm, that is 1 atmospheric pressure, is equal to 101,300 Pascal, and g acceleration due to gravity is 9.8 meter per second square. We know it this is fact from very earlier classes. Okay, dear students, we once again go to other table provided in the solution of this problem, where we will see that 1 atmospheric pressure is equal to 101,300 Pascal. Okay, so we move on to next table. This is the table. Okay, here we have used this. Okay, 1 atm is equal to 1.013 into 10 raised to the power 5 Pascal is equal to 1.013 bar. It can be written as 1013 into 10 raised to the power 2 Pascal. Okay, or if we eliminate this 10 raised to the power 5, then 101300. Okay, this figure will become 101300 Pascal. Okay, we will eliminate 10 raised to the power 5 as we have done in the solution. Okay, this is we have taken one atmosphere equal to 1.101300 Pascal. Okay, here we have eliminated 10 raised to the power 5. Okay, now using P equal to 0.050 ATM equal to 0.050 into, dear students, because when one ATM is equal to so many Pascal, then definitely so many atmosphere will be equal to so many multiplied with so many. Okay, so we will get P equal to 5065 Pascal. Okay, here in place of H we use the denotation D max which is provided in the definition. Okay, D max and H are equivalent terms, the maximum depth. Okay, dear students, depth, what is depth? Depth and height are equivalent terms. Depth is downward, height is upward. Okay, it is sufficient. There is no need to explain further. Okay, so H and D max are alternate terms. Moreover, dear students, density rho which appears in equation number 1 has two values with respect to this problem. Okay, one density is density of fresh water and the other density is density of sea water. Okay, so P equal to rho fresh water case 1 and rho equal to rho sea water case 2. Okay, two cases have emerged as a result of these two densities. Moreover, G is equal to 9.8 meter per second square, we know. Okay, dear students, in the presence of all this data, equation number 1 takes the form as under. Okay, so many Pascal is equal to this into this into this. From here we keep D max on one side and transfer all other data on other side of equality, and hence D max will become this. Okay, then this after simplification this and D max becomes equal to 0.518 meter. Okay, dear students, here we know that 1 Pascal in terms of Newton per 1 Pascal is equal to 1 Newton per meter square. Okay, and in terms of okay, this is m square and this is simply m. Here 1 m will be left. Okay, and all other values will be cancelled. Okay, kilogram will be cancelled out with kilogram, second square will be cancelled out with second square, and 1 m will be subtracted from m square and we will be left with the single m. Okay, so D max has become equal to 0.518 meter. This is equation number 2. Now we move on to second case in which other density is considered. Okay, so once again the same procedure. What difference? The only difference is that here in place of 998, okay, here in place of 998 kilogram per meter cube, we have taken 1500 kilogram per meter cube. Okay, which is the other density. Okay, in previous part we had used density 998, here we are using density 1500. So all other calculations are exactly same as in the previous. So it is sufficient to conclude that in this case d max alternatively becomes equal to 0.344 meter. This is equation number 3. Okay. Now difference in d max is equal to equation number 2 minus equation number 3. Okay. In equation number 2 d max is 0.518 meter, and in equation number 3 d max is 0.344 meter. So difference in d max is equal to equation number 2 minus equation number 3 equal to 0.518 meter minus 0.344 meter, and hence we are left with the result 0.174 meter, and this is the required solution of our problem. We have already discussed this table, so no further need to discuss this. We have also discussed this table. Now we come towards the reference book from where this problem has been chosen. Okay, dear students, reference book is Fundamentals of Physics Extended. Its authors are Holiday and Resnick, and Jarl Walker. Okay, so 3 authors. Okay, its publisher is Wiley, and its 10th edition having been published in 2014 or 11th edition having been published in 2018 has been adopted. Here chapter number 14 under title Fluids is our concerned chapter, and the problem which we have solved in this module has been enumerated at serial number 12 of the exercise given at the end of this chapter number 14. Okay, that is to say exercise number 14.12, and this is the end of our module, our problem. Okay.